So hi again, everyone. This week Ian's continuing his talk. So one second. Now he's continuing his talk, and
All right, everybody, welcome back. And so last week, just as a reminder, oh, Marion's. Oh, I have to just, there we go. Okay. I think she got muted. Okay. So the title of this talk was Extremal Graph Theory and the Problem of Zarankiewicz. But last week, I didn't even talk about the problem of Zarankiewicz. I just kind of give some background into the origins of extremal graph theory.
Hey, are you sharing?
Oh yeah, can you see the writing?
Okay, we see it in a tiny box.
Not sure.
maybe pin the video. There might be a way to pin it here.
Really not that used to it.
If you double click on that tiny little video, it'll enlarge it for you.
Okay.
Yeah, that's what I did. Not sure.
Let me see.
Oh, like, do you like can we go like large?
Oh, okay. Oh, okay. We're making progress. Hold on.
Okay.
Well,
That's weird. Video is
Can everybody else see the screen all right?
Yes.
we can only make it so big. We're on an Apple.
Yes, I can see it well.
They jinxed me and now I lost it too, but I'm sure I'll figure it out. It's fine.
Okay.
maybe we can, like come
There might be
access
some.
it. Okay.
Okay, like log in and
Right.
log out.
I think it's on the
Can we do that?
We may sign out and then sign back in because for some reason
Okay.
the window is it's just stuck on a small size. So let me try. Okay, so then we go back.
It's the same.
Oh, it didn't disconnect us.
Like maybe they can go again.
Okay.
I think it's because we already.
Yeah.
Well, we may just sit in the room with. Oh, yeah.
I'm really not sure. Maybe we should go like a small.
Just try signing out, signing back in again, maybe. It was a good fix.
Maybe should use it there soon.
Yeah, okay. It's just, see, it's weird. It doesn't even.
Is there a way to exit Zoom and then?
Yeah, like maybe you.
Oh my God.
That was the one.
Okay, sorry.
And now I guess.
in the upper right corner, there are some zoom controls that.
Okay.
That's not the one.
Okay.
Oh, there we go.
We can just slide. I'm so sorry, dude. Yeah. Okay.
So is everybody good now? Okay.
Stop video.
All right, perfect. Okay, so now that everybody can see the screen, I'm assuming you can see this writing happening. I just was remarking that last week, despite the title of this talk, I never actually told you guys what the problem of Zarankiewicz is. So we're primarily going to pick up where we left off last week and then hopefully end with this problem and kind of just talk about what is known and the vast amount of stuff that is not known about it. So last time we actually gave two proofs of Montel's theorem. Which determined the extremal number for a graph on n vertices that is triangle free. And it determined it to be n/2 ceiling times n/2 floor. And if you've forgotten what this extremal number means, it just means the the maximum number of edges in a graph on n vertices that does not contain any triangles. And by that, I mean just 3 vertices. They're connected like this. So I want to go back to where we began before we even did any proofs of Montel's theorem, when we just spoke about this extremal example, which turns out to be the unique construction achieving this extremal number. And that's the bipartite graph, complete bipartite graph on almost equally sized sets. And what you do is you just connect every edge here to every edge here. I think I've shot myself in the foot by not, but you get the idea. Every edge in this set over here, or every vertex in this set over here is connected to every vertex over here. You get a large number of edges, but there are no triangles because no 2 vertices in either of these sets are connected to one another. And so to pick up where we left off, we were talking about potential directions in which one might like to generalize Montel. And there are 2 seemingly natural ways one might like to try to generalize this. And it all kind of depends on how you look at the triangle. So we have this triangle. And in the one sense, the triangle takes a certain number of vertices, namely 3, and connects every vertex to every other vertex. So in one sense, it's a complete graph on 3 vertices, which is what this K3 means. But in another sense, you take 3 vertices and each vertex has exactly 2 neighbors. And so in that sense, it's a cycle, like you're just kind of cycling around. The orientation doesn't really matter, but that's the reason we call it a cycle. And so to generalize it, obviously you would try to make the number of vertices arbitrary. So I guess the reason it splits into 2 different generalizations is because when you have more than 3 vertices, say for example 5 vertices, the complete graph K5 and the cycle C5 look rather different, as you can see. And so when we're looking to generalize Montel with these cliques, as they call them, or complete graphs, one would like to determine the extremal number for n, k, l, where L is just any integer. I mean, if it's bigger than n, it's kind of not really an interesting question, but you're looking to compute this value. And for cycles, it's the same story. You'd like to compute x and CL. And as it turns out, let me go to the next page. The problem of determining x and KL has a very, very elegant solution. Namely, this was given by Turon in 1941. And I won't write down the exact number of edges, but essentially Turons theorem gives an exact value for x and KL. And as in Montel, a unique construction, what's called the Turon graph, should be T and this one, which achieves it. And in order to save some time, I've just gone ahead and got this this image from Wikipedia of a Turon graph. I think this is T13.5. But the general idea, and it's a very, very natural generalization of this extremal example from Montel, the complete bipartite graph, is you partition the n vertices of the graph into these almost equally sized sets. And if two vertices are in the same set, you don't connect them with an edge. And if two vertices are in different sets, you do connect them with an edge. So as you can see here, you will never have a K5 complete graph on 5 vertices, because in order for that to happen, you would need 5 different vertices, all of which are connected to one another. And this will never take place because by an elementary application of the pigeonhole principle, if you had 5 vertices, at least 2 of them would have to appear in the same, in one of these subsets, and so they wouldn't be connected to one another. And so the reason this theorem is so incredible is because it's one of the few cases where you actually get an exact formula for this, this value here. And once more, we have this unique construction achieving it. And so I just think it's very interesting how this direction of the generalization turned out so successful, but as we'll see, the other direction did not turn out quite as successful. And so Erdős actually said that Turons Theorem was the origin of extremal graph theory, not Montel's theorem, which I think is interesting because it's almost like Turon captured the essence of Montel with this generalization and made it very powerful. And the reason I say that is because, as I mentioned last time, Turon's theorem implies what's known as the Erdős-Stone and sometimes Szymonovich theorem, which gives an almost exact computation of X and H for almost any graph H. And so before I move on to talking about that, I'd just like to mention this other direction that we have, this other generalization with cycles. And so if Erdős-Stone Szymonovich, somebody trying to join?
No.
Okay. If Erdős-Stone Szymonovich determines this exact value for almost all graphs H, oh, sorry, cycle C6. For almost all H, I think I mentioned last time that when this number here is even, it turns out to be a very, very hard problem about which we know very little. So I guess the motivating question to continue this, to progress to the next stage of this talk is, why is this problem so difficult when this, this number here is even? And so I'm not going to prove the Erdős-Stone-Szymonovich theorem, but I'd like to at least, I'll just call it Erdős-Stone for now, because they're the ones that proved the theorem we're going to be talking about. I'd like to just talk about, kind of give some heuristic, I guess, intuition for why it might be true. So the Turon graph, as we saw on the last page, T k plus 1 is k plus 1 free, because remember, like in the case where we're splitting it, where this is a 5, you can never have a complete graph on 5 vertices, a clique on 5 vertices, because 2 of them would have to be in the same subset, and they would not be connected. So it's k plus 1 free, and obviously it has lots of edges. And for Turon, this was the extremal example he thought about and managed to show was the unique construction achieving this bound. Now, when we're thinking about, oh, and one more thing, the number of edges in a Turon graph, t and k plus 1, is greater than or equal to, but roughly 1 minus 1 over k times n choose 2. And to just kind of heuristically see this, you can think about it as taking all pairs between the vertices. And then since we're partitioning the vertex set into these k subsets and not connecting them, we're subtracting out all the potential edges that could come within these partitions, within these partition sets. So that's just kind of the heuristic way to compute the number of edges in the Turon graph. And that's all we're going to need for the purposes of this talk. And so what Erdős and Stone noticed was that if we look at this value, the chromatic number of a graph, which is defined to be, let's see, m, I guess, where m is the minimum number of colors needed to properly color the vertices of H. And by that, I mean that no 2 adjacent vertices have the same color. No 2 adjacent same color. So kind of an elementary observation that does require a bit of thought. It's not immediately obvious, but they would talk about in the undergraduate graph theory course is that chi of H is less than or equal to chi of G when H is a subgraph of G. And to see this, just note that any proper coloring of G is also a proper coloring of H. So the chromatic number of H cannot be more than the chromatic number of G, because the number of colors you use to properly color G also properly colors H in whichever example of a proper coloring you'd like to take. And so I guess what Erdős and Stone noticed was that from this follows that H is greater than or equal to the edges and when H, chi of H equals K, this extremal number, the largest number of edges in a graph, which does not contain H as a subgraph, is greater than or equal to the number of edges in the Turon graph, which asymptotically, well, I guess it would be an exact equality, is 1 minus 1 over k plus 1. And where O1 just denotes some function that goes to 0, as in goes to infinity, times n choose 2. And I forgot to mention this earlier, but once more with the Turon graph, note that the chromatic number is simply the number of these, the number of sets that you partition the set the parent set of vertices into, because you can color this set one color, this set another color, set another color, and this set another color. And you will never have two vertices of the same color connected to one another. And so the reason this here is true is because if the chromatic number of H is K, or should I say actually K plus 1, sorry. If the chromatic number is K plus 1, then this Turon graph with K parts always connected to each other can never contain H as a subgraph because the chromatic number of T in K plus 1 equals K. And so applying this identity up here, we see that H can never be contained inside the Turon graph, this Turon graph. So the remarkable thing that Erdős and Stone proved was that this bound right here is essentially the correct answer. So what Erdős and Stone proved, I'm going to go to the next page. Was that for a graph H with a chromatic number equaling K plus 1, or we don't even have to say that, we can just write, sorry, X and H equals 1 minus 1 over H minus 1 plus this little error term plus n choose times n choose 2. So this theorem has been called the fundamental theorem of extremal graph theory, and I think with good reason, because it determines this almost exact value for almost any graph H. And the reason I keep saying almost any graph H is the same reason why this problem doesn't help us solve, it doesn't help us find X C2L. And that's because when you have an even cycle, for example, cycle C6, the chromatic number is 2. And one can see this by taking blue, and then the two neighbors are red, and then blue, and then red again. And so applying this back into the Erdős-Stone formula, we get X and C2L equals 1 minus 1 over 2 minus 1. So 1. And since this value here is just going to become 1, these two ones cancel. And we end up getting that this value ends up being something like, oh, sorry. Which I guess tells us something. It tells us that, that this value is dominated by n squared as n gets very, very large. But that doesn't really give us as much information as we'd like, especially considering how much information we get when the chromatic number is bigger than 2. And so when your graph is either an even cycle like this or bipartite, since you could just color like this, and then there are some edges going between, the Erdős-Stone theorem doesn't really help us out too much. And so now I'd like to talk about this problem of Zarankiewicz, which was supposed to be, I guess, the centerpiece of this talk. Zarankiewicz was a Polish mathematician, which is why, and I apologize if I'm pronouncing it incorrectly for any native Polish speakers in the audience. So here's the central question that Zarankiewicz posed in 1951. For integers, less than or equal to s, less than or equal to m, and less than or equal to t, less than or equal to n, how many ones can be placed at most in a matrix M containing only zeros and ones, an M by N matrix M containing only zeros and ones, so that M contains no S by T submatrix of all ones. And so it looks like a pretty hard question. I think when Zarankiewicz first posed it, he was only asking for small values. So like if S and T were 3, 4, 5, I think it was just 3, 4, and 5 that he first posed it for. But it turns out that this number you're looking for, which we can call the Zarankiewicz number, Z M N S T. Turns out you can reformulate this problem so that it looks more like the problems we were talking about before, and it becomes an extremal graph theory problem. So reformulate. Instead of looking at this matrix, we can look at the incidence bipartite graph, and I'll explain what that means. Of M, which we can say is G M equals disjoint union Y E, where size of X is M, the size of Y is N, and X and Y are in E if and only if the entry in the matrix, the Xth row and the Yth column is a 1. And conversely, is not an E whenever XY is a 0. So the picture looks something like, we have this matrix of zeros and ones. Doesn't necessarily have to have any pattern to it. But we convert it, oh, and it's M by N, into this bipartite graph. We have vertices up here. We go from 1 to M. This is X, this is Y. And down here, where we go 1 to N. And if this is I and this is J, you connect these two vertices with an edge, and only if the ijth entry in M is a 1. So like here, if this were the ith row and this were the jth column, there's a 1 here, so then this edge would be put into our graph. Okay, and so before moving on, it's probably good to note that Z M N S T is not quite the same thing as the extremal number X N K S T, because when looking at ZM and ST, the parent graph in which you're trying to forbid this complete bipartite subgraph KST is itself a bipartite graph. And in the reformulation above, this is the bipartite graph I'm talking about. And this, when we're looking at X and KST, the parent graph is an arbitrary graph on n vertices. Okay, but they're both very interesting questions, and they're closely related, and many of the theorems about them have similar enough proofs to where people aren't too concerned about
So
the
question
difference.
before you
Go ahead.
go on. This problem, as it was originally posed, was in the graph theoretic setting, or was it just?
Oh, okay. So the question is, when Zarankiewicz originally posed this question, did he pose it in this reformulation below with graphs, or was it posed with matrices? And the answer is no. He originally posed it with matrices. So it didn't begin as an extremal graph theory problem, but people quickly realized that you could reformulate it like this.
So what was he interested in then?
I don't really know. I know he was a topologist and he did some stuff with graph theory, but I think in a general sense, this is just an extremal combinatorics problem that just deals with some, finite object in math, trying to maximize substructure within it, without something emerging.
Okay.
Yeah. Okay. Are there any other questions before we go on? Okay. Cool. And so both of these problems, determining Z, M, N, S, T, and X, N, K, S, T, are both largely unresolved. They're still very much open problems in most cases. And so we know very little about them, but we do know a little bit. And so shortly after Zarankiewicz posed the problem in 1951, 3 Hungarian mathematicians, Kováry, Sós, and our friend Turon from Turons Theorem and the Turon graph. And actually, it's a funny story. Sós is actually she was Turon's wife. So it's just a neat little bit of history there, I guess. In 1954, so 3 years after the problem was originally posed, they gave an upper bound. And I'm going to write it out. Oh, they gave an upper bound for both of these, I should say. And I'm going to write it out. It's not pretty, but as it turns out, the proofs are not actually that bad. I'm not going to do them here, but they're pretty believable double counting arguments, and they don't take anything too nefarious to see why they're true. To T is equal to N. Equal to S minus 1 to the 1 over T n minus t plus 1 times m to the 1 minus 1 over t plus t minus 1 to the times m. So this is the bound they gave for the Zarankiewicz number. And they gave a pretty similar bound for x and kst. 1/2 s minus 1 to the 1 over t n to the 2 minus 1 over t plus 1/2 t minus 1 times n. And so these bounds look horrendous, but when you actually start putting actual integers into them, they turn out to look somewhat reasonable asymptotically, as we'll see below.
So that kind of, I have half a question related to that.
Sure.
So asking if they're sharp is kind of nonsense because if s and t is supposed to be integers, then the
No.
right-hand side is an integer.
But that is a good question. So the
asymptotic
question,
sharp is the question.
yeah, so the question is, are these bounds asymptotically sharp? And as it turns out, they're known to be asymptotically sharp in two cases, actually.
So like for particular s and t or
When s, they're known to be sharp asymptotically, of course. When s equals t equals 2 and s equals t equals 3. And when s equals t equals 4, this is still unknown, whether these bounds are sharp or whether they are pretty far from the truth, which I think is very interesting. And so I have about 20 minutes. The last part of this talk that I wanted to do was just to go over what we know and maybe prove one of the lower bounds to show you just how insane things get for even s equals t equals 2. So as I said, these upper bounds, they follow from a fairly elementary double counting argument, some Cauchy-Schwarz thrown in there. But for the most part, the proofs are not too bad. Now, on the other hand, trying to match these upper bounds, and that is to say, constructing graphs with this many vertices, roughly asymptotically, which don't contain a KST, has turned out to be a very, very challenging problem. So what do we know? Oops. Oh, and before I go on, if anybody, again, has any questions, please feel free to ask now or just interrupt if anything comes to your mind. So, do we know? Okay, so the first bound, which I couldn't actually find a person to which this was attributed to, so I guess we'll just say mathematical folklore. But for infinitely many n, n to the 3/2 is roughly less than z n to 2 is less than or equal to, by the Turons theorem, n to the 3/2 plus n. And the lower bound construction here, it's similar to the one I'm going to talk about later, but it's not too bad. And that's probably why I couldn't find any authors to which it was credited, is because people probably noticed it rather fairly quickly, and it perhaps it wasn't insanely interesting to some people. I'm not too sure. And so the next one is due to Riemann, not the Riemann of the Riemann hypothesis, because this was about 100 years after his time, but a Hungarian mathematician named Riemann, 1958, so 7 years after the problem was posed. And he showed that for every n, x n k to 2, which I should mention, since we talked about even cycles being such difficult problems earlier, is the same thing as X and C4, because if you have a complete, if you have a bipartite graph on 4 vertices, it's complete, then you can easily translate it into a cycle on 4 vertices by sort of unfolding the crossing, I guess. So what Riemann proved was that for every natural number, this is less than or equal to n over 4 times 1 plus square root of 4n minus 3, which is horrendous, of course, but asymptotically turns out to be something like 1/2 to the 3/2, 1 minus some asymptotically very small function. And so this gives a slight improvement on the Kavarish-Turons upper bound for this specific case of K22. And the reason it's significant is because 5 years later, once more our good friend Erdős and Sós and Alfred Rainey, who is good friends with them, proved that for infinitely many n, x n k22 is greater than or equal to 1/2 minus n to the 3/2. So asymptotically, they essentially match the upper bound that was given by Riemann. And we will prove this. This is one proof that I'm going to do. Oh, and this was 1963. Okay. And then, so I mentioned earlier when Nathan asked the question that we know roughly the answer when S and T are both 2. And we also know the answer when S and T are both 3. And this is probably one of the most nefarious algebraic constructions I've ever seen to give the lower bound for this. It was given by Brown in 1966. He showed, 1/2 times n to the 5/3 times 1. So 1 is less than or equal to, this is Brown, x and k33. And if you go up and plug in the numbers in Kavarish-Turons, you'll see that it doesn't quite match their upper bound, but then 30 years later, Zoltan Ferretti, 1996, slightly improved the Kavarish-Turons upper bound to match Brown's lower bound asymptotically. And so, roughly speaking, when you're looking at x n k22, the exponent on the n, as you can see, looks like 3/2, 1/2 n to the 3/2. And when you're looking at x n k33, the exponent is 5/3. And so I have about a little under 10 more minutes. I would really like to do the lower bound given by Erdős, Sós, and Rainey, just so you guys can see how difficult the lower bounds for these problems are, and perhaps to suggest why nobody's come up with anything bigger than 3. proof will probably take a little over that. So if you want me to skip it, I
Go
can.
ahead, you got it.
Okay. All right, well, let's do it then. So proof of Erdős-Sarrey, which, just to remind you, says 2 is greater than or equal to 1/2 times n to the 3 halves. And so I mentioned earlier that these lower bounds often need algebraic constructions to come up with a graph that's very dense but doesn't contain these cliques. And as such, we're going to need a finite field for this one. So if you don't know what that is, that's okay. Just think about, behaves kind of like the rational numbers of real numbers, but there's only finitely many objects in this set that we're doing this algebra on. So let Q be a large prime power and set n to be q times q minus 1. Now consider graph where V is finite field on q elements minus the 0 cross self, but this time not removing the 0 element. And the edge set is given by pairs AB, CD, V choose 2, which satisfy AC equals B plus D, which looks incredibly arbitrary, but as it turns out, this is the graph we need to achieve that lower bound, that asymptotic. So quickly, you can notice that the size of V is q minus 1 times q, which is just n, because of course there are q minus 1 elements here and q elements here. And for a fixed vertex, some other vertex CD is in its neighborhood or is connected to AB. If and only if AC equals B plus D, if and only if, since A was defined to be non-zero, can take its inverse. So if and only if C equals A inverse times B plus D. And what this says is that for each D and Q minus the additive inverse of B, because then if D were the additive inverse of B, C would be 0, which would contradict the definition of the vertex set. So for each D, the corresponding, there is exactly one corresponding C zero, so that CD is in the neighborhood of AB. And in other words, what this tells us is that for an arbitrary vertex AB in this graph, the degree is exactly q minus 1. Because you can take the q minus 1 elements here and find exactly one other point which will work with them to be in the neighborhood. And so we end up getting exactly q minus 1 neighbors of every vertex in the graph. And so if we want to find the number of edges, we can once more use the handshaking lemma, which we talked about last time, to say that the number of edges is 1/2 the sum of the degrees of all the vertices. So AB, V, degree of AB, which equals 1/2 sum of q minus 1. And since there are n vertices in the graph, this is 1/2 times n times q minus 1, which, since n is q times q minus 1, is roughly the same as 1/2 n times q, which is roughly the same as 1/2 n to the 3/2, as n gets very, very large, goes on to infinity. So what this says is that we have the correct number of vertices, or the correct number of edges in the graph to match this exponent and even the coefficient here. So now all that's left to do is to prove that this graph does not have any k22s or c4s. So now we just need to show G is C4 free, which is the same thing as K22 free. Right. And so to do this, there are some messy computations, but the general strategy is to show that if A, B, and alpha, beta are two vertices, in V, then their neighborhoods intersect in at most one point. And to see this, note that if CD is in this intersection, then by definition, since CD is connected to AB and CD is connected to alpha beta, we have the two equations AC equals B plus D and alpha C equals beta plus D, which implies, just subtracting this one from this one, that C times A minus alpha is B minus beta. All right. Now, since by definition C is not 0, this means that A equals alpha if and only if B equals beta. Because if A equaled alpha, then this would be 0, and so this would have to be 0, and vice versa, because C is not 0. And so, since we assumed AB and alpha beta were two distinct vertices in the graph, this means that A does not equal alpha and B does not equal beta. All right. But now we have C from this equation up here. We have that C equals alpha minus A minus alpha inverse, since A minus alpha is non-zero, take the inverse, times B minus beta, which is non-zero, of course. And plugging back in to this equation up here, we have the D equals AC minus B. Or in other words, that CD is uniquely determined by the inputs A, B, and alpha beta. So CD, there can't be more than one CD in the intersection of these two neighborhoods. Is that clear? And so this is probably the most gentle construction. The other one by Brown ends up being in 3 dimensions, and it is pretty devilish, I'd say. I wish I had time to do it, but there's an hour that's been up, or the hour is up, I should say. And so I'm going to end it here and just note that this problem still has a lot of work to be done on it. As you can see, the lower bounds are quite difficult. Nobody's really given any substantial improvements on them since the 60s. There have been some here and there, but they're usually only in special cases, and they usually, they can be quite good, but as I said, they're usually only in special cases. So they don't really give us what we want, particularly KTT, just to begin, for any t bigger than 3. All right, and so that's it. Does anybody have any questions?
Well, let's first thank our speaker. And I have a few, but maybe just one questions first.
Okay,
Yeah, so I had a question actually.
sure.
Could you go back to what was Turons Theorem? What did it actually say? That was a
Oh,
little bit
okay.
unclear.
I can give you the exact statement, actually. Well, that's probably not a
Did
good
it just
idea.
give you an asymptotic lower bound to the extremal problem for clicks, or did it actually give you the extremal graph?
Oh, so Turons theorem gives an exact value for the extremal number for clicks, and this unique construction achieving that value. The same way that
Okay,
MOMS
so-
will give exact value for triangles and a unique construction achieving it.
Okay, cool. So, but Erdo-Stone and sometimes Simonovich theorem gives you an analog of this result but for arbitrary subgraphs, right?
Yes.
Yeah, okay. And what did you have any particular conditions on H, or was it like, is it on a case by case basis? Like,
No,
you said
the only thing you need to know about H is the chromatic number, which of course is not usually a very easy problem, but
I see, okay.
if you know the chromatic number and it's bigger than 2, then you can get an almost exact value for H.
Okay,
for
okay,
X.
I see.
Yeah.
Okay, yeah, so that was just basic questions. Thank you.
Anyone else? All right, if no one else has questions, you can go
My
ahead and
turn.
fire Nathan.
So I have a few. So the first is, I think it was the this bound for T or KTT, I think it's called.
Oh, at the end?
Yeah, so 2, 2, it goes asymptotically at end of the 3 halves, yeah?
Mhm.
3, 3, 5 halves is the conjecture that it keeps increasing like that, so.
Oh yeah, Erdős actually put out a conjecture. I think he put money on it. It was one of Erdős's problems that he put up for like $100 or something. They conjectured that there's some sort of pattern here, because I think, as Nathan was saying, where we ended up writing it down, we can observe that for 2, the exponent is n to the 3 halves, and for 3, it's n to the 5/3. So I guess they conjecture that there's a sort of general pattern here, but as I said, nobody's really found anything for K44 even.
So Brown's proof of, I guess, the lower bound, does it mimic the idea of this finite fields proof, or is it something completely different?
So Brown's proof is, Nathan asked if Brown's proof mimics the one given by Erdős, Schoch, and Rainey. And Brown's proof does involve a vector space over a finite field, and it's sort of geometric. Well, I didn't really want to get into this too much, but one can kind of think about this problem or the construction of this graph as taking points and lines. So you have a point in this plane here, and then this is sort of a linear equation, sort of. And in this finite geometry, the calculations aren't too bad. It turns out that for each line, three distinct points determines a unique line. And so if you have 2 points, like these 2 points A, B, and alpha, beta, then if they have a third point in common, they would have that line. And if they had a fourth line, or sorry, another point in common, then they would have 2 different lines. We would have 2 points that are both on 2 distinct lines, which in this finite geometry turns out to mimic Euclidean space, the Euclidean plane, in the sense that you can't have 2 distinct points that are on 2 distinct lines. So then in Brown's proof, he ends up looking at unit spheres in 3 dimensions, a 3-dimensional finite geometry, and it gets pretty crazy. We can talk about it afterwards if you'd like.
Okay, so but it's almost like an algebraic geometry kind of construction to prove finite field,
Yeah.
something like that.
And actually, people have been looking for the two constructions are not very similar at all, which is why it's been so hard to get anything bigger. They both use this sort of finite geometry, but they're quite different. And it's actually, people actually think that it might not be possible for 4.
Okay. Yeah, because the proof was like it's something I definitely never would have thought of.
Yeah, it's utterly ingenious. And then Dr. Nagel commented, the suspicion is that Kavary-Shoshtouron is the right order of magnitude, but that the constant is probably wrong. So,
Okay.
oops, that was, okay.
So I have a few more questions, but maybe I'll ask later because they're less specific to this talk, more just about general extremal graph theory, I guess.
Sure.
So cool, I guess let's thank our speaker one more time. And I don't know that we have a speaker for next week. I think Nina said she wanted to speak.
Here.
But I'm sure she wants to delay. If someone else would like to speak, let me know and we can arrange for it. So let me stop the recording.